Good morning, friends. It gives me immense pleasure to be here again for my course, that is flight mechanics. I am in my last phase of this lecture series. As of now, we have discussed about flight mechanics different modules. In module 1, we were discussing about introduction to airplane performance, and we know that in airplane performance the two parameters are very important, that is lift and the drag. In our module 1, we have seen that lift is equal to half rho v square s, d is equal to drag is equal to half rho v square s cd, L is equal to half rho v square SCL. The CL and the CD are very important parameters in this aircraft performance, and to generate this lift or the drag, we need to understand about atmosphere. So we have understood the atmosphere also, and in module 2 we have discussed about cruise flight. In cruise flight, that is steady level flight, where lift is equal to weight and thrust is equal to drag. So these two forces, that is weight is countered by the lift, which is perpendicular to the relative velocity, the lift, and drag is parallel to the relative velocity. And this drag has to be countered by the thrust of the aircraft. And module 3, we have discussed about climb flight. In climb flight, climb angle, rate of climb, these all things we have already discussed. Today we are going to discuss about some questions and answer from the question bank of our Institute of Aeronautical Engineering, Department of Aeronautical Engineering, Hyderabad. I am Dr. Yagya Dutta Dwivedhi, Professor from Department of Aeronautical Engineering. Today I am going to discuss about introduction airplane performance, discussion on question bank and its solution. So there are a number of question bank in this. So we will see the first question number 1. What is the off standard and the design standard atmosphere? How these two are different from each other? Explain with suitable examples. We know that the standard atmosphere, that is ISA, internationally it is by the sounding rocket, by some balloons. Everywhere in the world we are making and measuring the pressure, temperature and density, rho, and we are making the tables and variations of the P, T and rho. These are always used for the standard measurement. But sometimes whatever given in international standard atmospheric table, it may not be exactly true. Suppose, example I am giving, we are at here sea level, aircraft is on the runway, like this, it is on the runway, and at sea level it is rho is equal to 1.225, standard atmosphere 1.03 bar pressure, and temperature is 288.06 Kelvin. But if it is somewhat away from the sea, like in Hyderabad, the distance is approximately 353 from the meters from mean sea level. So here all these parameters will not be same. So this condition, the actual condition from where the aircraft is operating may not be same. That is called off standard. In design standard, these are the design standard. In ISA is the design standard, and if we deviate from the design standard, it is a off standard. And in this way they are differing, explained with, I gave the example also. So in this way question number 1 is done here. So this we can further, this we can see here that the International Standard Atmosphere is a static atmospheric model of how the pressure, temperature, density and the viscosity of the Earth atmosphere changes over a wide range of altitude or elevation. It has been established to provide a common reference for temperature and the pressure, and consists of tables of values at various altitude plus some formulation by which these values were derived. The International Organization for Standards publishes this ISA at an international standard. Now I will discuss about the question number 2. What are the parameters are measured by air data system? Explain the techniques to measure this data. So we have, in aircraft we have a lot of equipments like airspeed indicator, altitude indicator, roll pitch indicator, artificial horizon, artificial gyros. These all are the equipments which are operated by the help of the air. So this air which is entering in the sensors, these are taken by the system, by the computer. So this is called the air data system. So here we will see that air data computers are used by aircraft to acquire and process data from pitot and static pressure sensors, databases and analog input to obtain key air data parameters such as altitude, airspeed, high deviation and temperatures to ensure safe and accurate flight on both rotary and the fixed wing aircraft. So these data systems are used by the aircraft to acquire and process data. So suppose this is the aircraft. This aircraft is okay, so this is the rudder. Here is the elevator, and here we have the ailerons. Here is the pitot tube. Sometimes in the wing also this pitot tube is fixed here and here. So this air is entering here. This air may have the some, as per the altitude, their density will be different, temperature will be different, and these all parameters. Here just you can see here, we have the front large area display, rear large area display. Here we have the navigation ADC, sensors, radar, communication VHF, UHF and other equipments are there. So these all pressure sensors which will fed to the computer, and they will give the signal to the different systems like navigation, communication. All these things will be performed by the help of this data system, and this is used, a pitot tube is used to do this all work. Now I will go for the question number 3. Plot the international atmosphere with elevation and temperature. Explain salient feature of this plot. So just now in the first question I explained you that there is an international atmosphere, ISA, international standard atmosphere, and in that the variation of the elevation or the altitude with respect to the temperature and density and pressure is plotted. So we are going to discuss about this. This is the plot which I have taken from the net. International atmosphere, here is the pressure in kilonewton per meter square. Here is this is the geometric height, and here we have the temperature in this zone. If you see here, we have the first is the troposphere, it is the lowest part. Then we have the tropopause. Then we have here stratosphere. Then stratopause. The pause means it is the boundary between present one to the next one. Mesosphere. Then mesopause. Then thermosphere. It is the, then last is the Kármán line. So here if you see the temperature at 0 means it is minus 273 Kelvin. 100 means minus 173. It is at 27 degrees centigrade. So if you see here, the up to troposphere, this is nearly 11 kilometer. This point, it is a troposphere. If you see in the troposphere, as the altitude is increasing, temperature is decreasing. If you go to the stratosphere, up to sometimes it is constant, and after that temperature is increasing up to stratopause. From the stratopause, if you reach to the mesosphere, in mesosphere again the temperature is decreasing, and this is up to nearly 85-87 kilometer. This is the shown here. So here we can see that the relation between temperature and the altitude is always varying. It is not the constant. So in the stratosphere it is falling down. In the mesosphere up to some distance, nearly 30 kilometers, it is constant. From 30 to 5 it is increasing. From 50 kilometer to nearly in ionosphere it is decreasing temperature, and further it is thermosphere where everything is. So here if you see here, all these altitudes are given here. Here is the death zone, that is the Mount Everest is nearly somewhere 8.8, nearly 9 kilometer. It is the Everest here. So we can compare with Everest. Everest is in the tropopause only, and there is a atmospheric limit. Here we have the, in stratosphere we have the ozone layer. Ozone layer is found nearly 30 kilometers. So this way we can plot the international atmosphere table with elevation and the temperature. Now the next question, explain about the true airspeed, indicated airspeed and calibrated airspeed. How these speeds are compared with each other, which one is the most suitable for aircraft performance. So here different types of speeds, that is the TAS, true airspeed, indicated airspeed, and the calibrated airspeed we have to discuss. So we can see that the true airspeed, it is also denoted by TAS, is the measure of the speed of an airplane in relation to the airflow around it. This can vary with differing types of air density, and as you know, you may know air density can vary at different altitude. Just now I have shown as per the altitude your density is. So true airspeed, the actual airspeed which aircraft is experiencing when it is flying at different altitude, because density is varying. So everywhere their lift value, their drag value, all will be varying. Indicated airspeed, this is especially important as it indicates the bounds, that is maximum, minimum and the maximum airspeed that the particular model of the aircraft is capable of safely operating within. So indicated airspeed is indicated in the instrument panel which pilot will see. It is very important because this will give the limit, because there we put some green, yellow, white and at the last red. So if it is the red means you are crossing the limit. So we should not cross that limit. We should always fly in the green zone. There is a yellow zone and then first is the white zone. This white zone indicates that you are in the lower limit. That is the minimum limit. We should not go below this white point. So these are the true airspeed and the indicated airspeed. Third one is the calibrated airspeed. This includes or accounts for any position error that an aircraft experiences. Due to the position of the aircraft, due to its different instrumentation, there may be some error. That error has to be calibrated, because the true airspeed is the actual airspeed, but indicated airspeed which we see on the cockpit. The pilot will see on the cockpit, there is a instrument that is called IAS, indicated airspeed, IAS, and here we have 0 and here we have the some maximum, maybe of 500. So up to here it is the white, then it is a green and then it is a red. This is the lower limit and from here this is the high limit. So this is indicated, but this has to be calibrated. Your instrument really how much it is showing, this has to be calibrated. That is called the calibrated. Calibrated speed is the error corrected speed. So this lift to drag ratio is very important parameter. So if you see that L by D, we can also write CL by CD, and we know that CL and CD is equal to CD naught plus KCL square. So if you see here that L by D ratio is depend upon the drag and this CL square, and if we put this value here, CL is equal to 2 W by S rho V square. Here also, so if you see here that rho W by S rho V square plus K into 2 W by S by rho V square whole square. So if you see here, if you take this common, so you will get 1 by 1 plus K W by S rho V square. So this is the L by D ratio of the aircraft. It is depend upon the weight, then area, rho and the velocity. So this you can find out in this way. Describe for skin friction drag of an airplane. A. The physics of the generation, how it may be estimated, measure to be taken for its reduction. So here, first, what is the skin friction drag? So this skin friction drag is the drag which is skin friction drag. It is the drag which is making aircraft to move, to stop or to restrict the motion of the aircraft due to the friction, the viscosity. So if I make, this is the airfoil and this is a part of the parasite drag. So if this is the airfoil and this airfoil has got some friction here, it is not very smooth. So as and when this goes, due to this aircraft, this start, it will not be attached. Here some vertices will be formed due to the friction. It is happening and this is called here the separation point. This is called separation point and these are the vertices. So here the kinetic energy of up to here is sufficient, and here is the pressure energy which is pushing. So here is a pressure energy, and it is also called the adverse pressure gradient. So this adverse pressure gradient is pushing, and this kinetic energy is pushing. So there is an equal point. There flow will be stopped. This is called the flow separation point, and from here flow will not be attached. This will generate the friction that is called the skin friction drag. And in this way, it is a physics. And how it can be estimated? This can be estimated by its coefficient of friction. If we use it, we can estimate measure to be taken for its reduction. So how we can reduce? How we can reduce this? So first one is the vortex generator. Second is the pumping air, suction of air. So these are the things which used for this. And what is this vortex generator? If this is your aerofoil, your flow is going from here, and it is separating here, then what we do is, in this point we will make the vortex generator like this strips. So air will enter from here, and it will act as a nozzle. The kinetic energy of the flow will increase, and this will further push forward. So in place of here, now if you put this thing, it flow will go up to here, and then it will. So this much wing is used for lift generation, and drag will reduce. There are some more techniques, but for skin friction we have this much. Otherwise, if you induce drag, we can use the winglet, and some other things are also used. Now describe with the help of a diagram the mission profile of a civil transport aircraft. What is involved in performance estimation? So if you take the civil aircraft, so it is first from here to here, it is on ground. Engine will start, it is called the warm up, then it will move on the ground, it will reach to the end of the runway here. From here it will start climbing, that is initial climb, then it is a first climb, then it is a second climb, then it start the cruising. We have the first cruise, second cruise, and the third cruise. As per the different range of the aircraft, this cruise will be performed. Then after near you are reaching to the next destination, your aircraft has to come down. This is called the descent. From here, aircraft will land. This is called approach. This is called the approach here, approaching, and then this is the runway, and here aircraft lands. So these are the different mission profile for the passenger aircraft or transport aircraft, which normally we fly for the one place to another place. Explain with neat diagram about aircraft force system during straight and the level flight and during pitch up at 30 degree. Explain with a neat diagram about aircraft force system during straight and the level flight. So we will see here that if this is the aircraft, This is the rudder. This is the elevator. These are the ailerons. These are the flaps. So if you talk about the force, so we have the four forces. Just I will draw with red color. So this is the weight, this is the lift, this is the thrust, and this is the drag. So these are the four forces which are used. So lift, weight, thrust, and the drag. These are the four forces which are used for the. Now if we make this same aircraft with the 30 degree, then what will, so just I will, this is the horizontal and this is the 30 degree. So here is the your aircraft. Just I will draw the aircraft like this is the aircraft, and so this is the 30 degree. So what are the forces acting? We know that if aircraft is moving in this direction, lift will act. I will draw by the red color again. So lift will act perpendicular. So this is the lift. Drag will be always in the same direction. This is the thrust and this is the drag. So here if you see, this is also 30 degree. So W cos of 30. So here lift is equal to W cos of 30. So in this case, your lift will be less than the actual weight. So that is the difference between the 30 degree and the straight and the level flight. So determine the temperature at 20,000 feet and 50,000 feet altitude, assuming ISA condition. So this we can see at the 20,000 feet, this altitude is located in the first layer, that is the troposphere. So we can write here that TISA is equal to T naught plus LH. T naught is equal to 288.15 minus, this is the L, that is the your gradient, 0.002 into 20,000, you will get 248.15 Kelvin or minus 25 degrees centigrade. And the same way, if you do at 50,000, you just put this value here and you will get here minus 56 degree centigrade. Another, this numerical too, the temperature in a city on a summer day is ISA plus 2 and on a winter day it is ISA minus 25. Determine the temperature on both days in Celsius. This city has an elevation of 3,000 feet. So you have 3,000 feet. We have to find out the temperature in Celsius. So we know that TISA is equal to T naught minus LH. T naught is equal to 15 minus 0.002 into, so you will get the 9 degrees centigrade. In summer days, T is equal to ISA plus delta T. So 9 plus 32 here, 41. And in the winter days, it is 9 minus 25. You will get minus 16 degrees centigrade. So the next question, determine the pressure of air at 40,000 feet in ISA. In ISA condition. So since this altitude belongs to the second layer and it is unit is in feet, we have to use this equation that PISA by PA and 0.2234 exponential 36.089 minus h by 20 point. So you will get this, you got this PSA. So determine the density at a 5,000 feet altitude and in ISA condition. So we know that in ISA is equal to T 5,000, TA minus LH 15. So you will get this air, the air pressure P by P air is equal to T by T naught. So you will get these things, you will get the density and other parameters. So in the next lecture, we will discuss about discussion and the question bank solution and the cruise flight. These are the references. Anderson JD, Aircraft Performance and Design, International Edition, McGraw Hill's first edition, 1999. SL by ME, Aircraft Performance, Theory and Practice, AIA Education Series, AIA 2. Any questions, you are welcome to ask. My email is yddwivedhi@gmail.com. Okay, this is my email. You are please welcome to us. Please do like and subscribe this channel, and do the comments, because if you have any problem you are not understanding, I can explain this thing. Please do not forget to click the bell icon. Till then, thank you and goodbye.
Like, share and subscribe. Hit the bell icon for more updates.